Good morning, everyone. I'm really happy to see so many people here. I'm really happy to see so many friends of Bore who manage to this meeting. So I'll chair the first session, and we start with a presentation by Jan Olof Nielsen, Stainless Steel Development from Qualitative to Quantitative Science. Thank you very much.
Good morning, ladies and gentlemen. It's an honor to be here this morning. This is an homage to Börje. Our collaboration started in 2004. I provided some interesting problems, industrial problems for Börje, which has resulted in some common papers. And I will give you a few examples of the output of this collaboration. Steel has a very long history. This particular example is taken from the Qutb pillar in New Delhi. It's a pillar which is 1600 years old. It's a very good example of forge welding, so to speak. But what is most interesting with this pillar is that it has not rusted. It's 1600 years old. There is a passive layer on the surface, but it has not rusted. Another very interesting example, an ancient example, is from the terracotta army. 2,200 years ago, people were able to produce stainless steels. It's chromium plated. It's amazing. So with empirical knowledge, mankind has been able to produce very good steels for a number of years. (1985) is a very important year because this is the first time that a stainless steel or a steel of any kind is optimized using computer-aided alloy design. So the tools that we have available today are much, much better and much more quantitative than they used to be. What are the tools that we have available? Well, there is a number of experimental tools, the light optical microscope, of course, but also various kinds of electron microscopes, such as the transmission electron microscope, the scanning electron microscope. Glow discharge optical emission spectrometer is another tool. Atom probe field ion microscopy, by which you can identify adjacent individual atoms. But also a number of computational tools, such as Thermo-Calc, which became available in the middle of the 1980s. And the last few years, also density functional theory, which has actually aided and assisted developers of stainless steels. I will give 3 examples today. One example is taken from the duplex stainless steel SAF 2507, which is the first alloy ever to be developed and optimized using computer-aided alloy design with the help of Thermo-Calc, an early version of Thermo-Calc. The second example is taken from the stacking fault energy. It's now possible to calculate the stacking fault energy from first principles. And the third example is from the well-known miscibility gap in the iron-chromium system, the ferrite which becomes unstable under certain circumstances and leads to embrittlement. When a steel is not optimized, such as a duplex stainless steel, one of the components is more sensitive to corrosion than the other. So an important task for the design engineer or the alloy developer is to optimize the ferrite and the austenite so as to achieve equal corrosion resistance in ferrite and austenite. This was accomplished in 1985 using an early version of Thermo-Calc. I don't know if John Ogren is here, but this was a collaboration with him in 1985. The first alloy, not only in our company, Sandvik, but the first alloy ever to be optimized using computational tools. This is what happens to austenite. Austenite here is more sensitive to corrosion. So there is selective corrosion of austenite. And this is definitely not optimized. This here is an optimized structure. The second example is from stacking fault energy. A stacking fault is created when a lattice dislocation is dissociated into two Shockley partials. And in between these partials, there is a stacking fault, a local HCP structure. The stacking fault energy is a very important parameter in materials science, in the behavior of materials, because the stacking fault, the two partials have to constrict in order to cross-slip. And the lower the stacking fault energy, the more difficult is this process. And this leads to work hardening. A low stacking fault energy leads to a high work hardening rate. So it's a very, very important parameter. This is now possible to calculate. It's difficult to measure experimentally, but it's possible to calculate. And this is one of the examples, I would say, that where the calculations, theoretical calculations, from first principles, are much more accurate than the experimental results. And there is a very good, considering the inaccuracies involved, there is a very good agreement between the theory and the experiments. This is an example from the iron-chromium system in which we have a miscibility gap here. The ferrite is unstable and dissociates into iron-rich and chromium-rich ferritic regions. And this leads to so-called 475-degree embrittlement. And understanding this instability in the iron-chromium system is very, very important in developing and optimizing alloys. And presumably, hopefully, it's possible to suppress this mechanism. But in order to do so, we have to understand this from the we have to understand the fundamental processes. It leads to embrittlement, as you can see here, from the aging temperature versus aging time. The process is most pronounced at 475 degrees, but it also occurs at lower temperatures, albeit at a lower rate. This can be visualized in the transmission electron microscope because the elastically soft regions are the 001 directions. So the strain is largest in the 001 directions. So if you orient the crystal exactly on the 001 zone axis, then you see a diffraction contrast. So the mottled contrast that you see here is actually is a sign of the 475-degree embrittlement. Börje's group has contributed to a deeper understanding of the embrittlement and the so-called spinodal decomposition in the miscibility gap. Mats Hillert at KTH, he in about 50 years ago, he approached the problem from thermodynamics, and he was the first one to actually understand the basic principles of the 475-degree embrittlement and the so-called spinodal decomposition. Very recently, it has been possible from first principles to calculate the enthalpy of mixing here as a function of the chromium concentration. So in the ferromagnetic state, we have this curve, theoretical curve. However, if we use disordered local moments, we can actually reproduce the experiments very, very well. And this is very recent work performed by Pavel Konjavi and co-workers in Börje's group. So this has led to a deeper understanding of the spinodal decomposition. And this is very, very important because a deeper understanding helps us to optimize alloys. And hopefully this will lead to knowledge that helps us to suppress this phenomenon. So this is the conclusions. Alloy development has for a long time been empirical. I would say up to the 1970s, the 1980s, alloy development has been empirical, phenomenological, qualitative. It's now much more quantitative. Thanks to thermodynamics, the way in which thermodynamics is used to optimize alloys, but also very much thanks to the fundamental theory, first principles calculations, DFT, and so forth. So this has contributed to a better understanding of the stainless steels and will lead to alloys, optimized alloys in the future. Imagine what you can achieve if you're a good violinist, what you can achieve with a Stradivarius violin. A violin has 4 strings, but the periodic system has more than 100 elements. So imagine what you can achieve with all these elements. So the ocean is open in front of us. Thanks.
So, good morning, everyone. I can really tell you this is a big honor and a very special thing to be talking here. Really, in many ways, when I first was approached to talk here, I got a comment that I should be talking about the development of theory and how that has influenced the materials development. This is certainly nothing that I can do. I have, in fact, never really published a theoretical paper. I have also never published together with Börje, so I have not really seen how that has been going on. On the other hand, I feel very, very happy to talk here. And then when I also looked into the program and saw who would be speaking here and what they would be talking about, I realized that they were much more qualified to talk about these things than I am. So I will talk about this in a little bit different way, about physics, about materials, and Börje, how he influenced that from my point of view and the way I look upon it. Börje, he is really the physicist for me. He was the first one really introducing me to physics. In many ways, and I will come to that. He is also the teacher, one of the most inspiring teachers that I had, and in fact the only teacher where I kept and still keep the lecture notes from. Moving around, you throw these type of things away, but I still keep that one. Certainly his influence upon materials has been enormous, and it's way more than I can cover. But he also has been what I would call a scientific evaluator, and he influenced a lot about the Swedish policy about science evaluations, and things that comes together with trying to understand science. Maybe in some way he was way ahead of the Chinese in introducing various types of ranking systems, not formally, because certainly he is not a formal bureaucrat, but in the way that he influenced the Research Council. And so, last thing, he's a very special person. He's one of those persons that you really can discuss with. The first time I heard about Börje was when this paper should come around. It was the calculations of the phonon spectrum. I happened to be at that time an undergraduate student trying to do my diploma work in Studsvik together with Ingvar Ebbsjö. And Ingvar came back. I mean, he was sitting in the room not next to mine, because I'm coming to that person later, but he was coming and said, oh, I have been in Stockholm. I met two persons that were really something very extra, something very, very special. And one was Börje, and the other one was Anders Rosengren, who might be somewhere around here. And he tried to tell me a little bit about what they were doing. And clearly, I mean, it was a very magical moment, because it was something that was really inspiring. And I mean, you see this paper. This was published August 15, and it was received by the editor in March. And at that time, this was way before internet. I mean, you have to be aware of at that time, I mean, reviews were sent out, I mean, by ordinary mail, and they were sent back by ordinary mail. It was not something you were downloading on the internet. So it was something very different. So when Börje talked about this, and Ingvar talked about this, I mean, the thing was that the person that was sitting between me and Ingvar at that time was Ivar Waller. Yes, it's the Waller with the bi-Waller factor. At that time, I didn't know that he was a Swede, actually, when I started there. So, I mean, for those of you who are not really familiar with Swedish history, Ivar Waller was certainly a Swede. So then I understood that this must be something very extra in life. Börje as the teacher, when I then started on as a graduate student, my next encounter with Börje was when he was teaching the classical electrodynamics to me. I think it's the only physics course that I tried to understand, really, or I had to understand. And it's still the only physics course, I mean, where I still keep, I mean, the book, I mean, in the best bookshelf that I had. And this was, of course, Börje's. It was an inspirational set of lectures. So sometimes, I mean, knowing what we are going to talk about later, I'm sometimes a little bit surprised with your interest in your developments in electromagnetic theory. I'm surprised that you didn't move about 50 kilometers south, ending up at the ABB in Ludwig, developing that type of thing. It was really something special. When it comes to materials, I tried to go through a little bit about what...
Microphone, please.
Microphone.
Stand there, don't go away.
Oh, have I agreed to that? Have I? So when you talk about materials, I mean, and you start to look upon what type of impact Börje has had in various ways, I mean, you can see that this list is quite long. And this is certainly areas where he has been publishing. I have actually checked all of this because, I mean, I happen to get some information some other way, and I realized that this is something where he has been working. I mean, if you would put in my contributions or something like that, you maybe, in the very best case, you could pick one or two of these areas. So this is something. So, I mean, to try to cover this, who can do it? The science evaluation part, which I'm coming to and which I think is important. When I started to work with science and science evaluations, it was in the old time of the NFR. It was at something which was at that time called the Physics Committee, the Program Committee for PUF. It was, I mean, the condensed matter physics, that part. And I mean, then it was a different type of training. It was a different type of setup of how you evaluated science. It was a discussion about qualities of ideas. I mean, actually, I mean, to start counting publications, and I mean, trying to understand the impact of publications, the impact of what you have been doing and what you are doing today. I mean, this was in some way partly new to a lot of people. So, I mean, those lists that we hear about, the Xiaotong list, I mean, the Shan from Shanghai, I mean, and the various type of rankings, was in some way introduced in an informal way in this type of groups. And I will very much remember the very first meeting that I participated in. Börje was sharing this one. It was in Uppsala. Quite a long time ago. It was such a long time, so Rajiv, who is now, I mean, the most valuable colleague and the most valuable physicist, was actually making the coffee at that time. So you had you can understand that this was some time ago. But by the way, I mean, you are very good in making coffee. You kept us all awake until 4 o'clock in the morning.
But I didn't get money.
So, I mean, certainly that was something really different. I mean, and what you started to do at that time was, I mean, you had to go through all these evaluations. Börje was sharing this one. We were about, I mean, at 4 o'clock, we went back to the hotel room, realized that, I mean, we had about 5 times as many applications that we wanted to grant it that we had money. And we had to find out the solution. That was really something. That happens a couple of times later, but it was really a training about science. But for those of you who believe that Börje is only involved, I mean, in theory, I mean, you are completely wrong. I mean, Börje has also been very instrumental in these big developments of large research infrastructures. He's been part of the discussion around the MAX laboratory and the MAX 4. Last week, we had a meeting here at KTH because Mikael Eriksson was granted the big prize at KTH. Mikael Eriksson was the developer of the MAX 4 laboratory, the accelerator physicist. I would say one of the most important persons in that process. And at that time, it was, of course, it always comes up when all people, it was a discussion about the Berlin meeting, where you obviously participated very much. I mean, because Anders Flodström was there, and then it was a discussion about how that was done, and I mean, the development of the MAX 2. Another time that I met you was when back a long time ago, when you were in the board of MaxLab, around 1987, 88, I was driving you, I mean, down to the... So that was something that I know firsthand. I mean, we also know that you have been quite involved in the European Spallation Source. You have been the representative for the European Spallation Source a couple of times. You've been writing articles about the need of developing neutron scattering, the developing, I mean, these infrastructures, and certainly about computers, I mean, clearly. But of course, for being a theoretician, I guess that is natural nowadays. The other part which I think is really important when you look upon this is the discussion about internationalization, which started quite early. I mean, to really realize that science is an international area. Exchange of students, exchange of scientific researchers, which we see today. I mean, many of the speakers and many of your guests are colleagues and the friends from foreign countries. Certainly something where you were ahead of time, at least in Sweden. But then there is, of course, Börje, the very special person. The person, and I mean, there are a couple of things that I think we should point upon here. I mean, first of all, it's the way he cares for his family and friends, which I have, and I count you as one of my friends. And I mean, many of these times, I mean, you realize, I mean, what kind of person he is. I mean, quite a unique person, taking care of people, knowing about people, thinking about people. So that is something very important. The other thing that, of course, comes up in is the discussion about Dalarna. I was home on Mother's Day this year, because my mother is still alive. And, of course, what he had picked up was an article in Ludvika Tidning about you, which is quite an interesting thing. So I was reading, I mean, that is something, an impact. Many of you would probably not even know about Ludvika. I mean, it's a town in the southern part of Dalarna. Some people would say, I mean, that you are from Dalarna, you are Rumpmas, but this is certainly wrong, because that is the people from the Avesta region. So be aware of that. So, I mean, in that way, I learned about things like Solvarbo, Gustavskorv, and Moje, where I have been visiting you. And of course, I knew about Gustavskorv way before I met you, because it was something that I was eating when I was a kid. So certainly this has been something. Other things that, I mean, is very interesting when it comes to Börje is his interest in sports. And I mean, being a little bit critical or surprised, I mean, I'm a little bit surprised that we have this meeting today knowing, I mean, that Sweden is playing Ukraine tonight.
He already mentioned that.
Oh, that was before I came in. I mean, because when it comes to sports, I mean, something can happen. I mean, especially when you have the Leksand ice hockey team playing and so on. I mean, suddenly, I mean, you can have a telephone call, and this telephone call you can hear. I mean, you'll take off the receiver, and that this is from way, way far away. And it's Börje calling. So, what was the score? I don't get them into the internet here. This interest, I mean, for sports, the interest for ice hockey and so on, is something that I think you should be very well aware of. And knowing, I mean, what's going to happen tonight, I mean, I will look forward to this in a very special way. So I just want to finish this one with saying thank you very, very much, Börje. Thank you. Thank you for everything you've done for me. Thank you for the things you've done for Swedish science and Swedish physics. I'm very happy and very proud to be talking here. But I wasn't talking about the subject that they told me to do, because I'm not qualified for that. Thank you.
Okay, thank you. It's an honor to get invited to this occasion. I thought, when did I meet Börje first? And I think that was in connection to the Research Council. And it was this kind of meeting with an evaluation panel. And then the people, they came with their briefcases with papers. Now it's only one Börje here. It's not two. And, but Börje, you did not bring any briefcase with papers. You brought a suitcase. And it was not a small suitcase, it was very large. So what did you have in the suitcase? So that was the first encounter with Börje. And the next was also in connection to a research council. And that was this kind of little new with they also added strategic research. And we had a program there, a program in material science called Atomics. And you are the father of that name, if you remember. And also you were promised a bottle of wine.
I got it.
You have got it. Yes, you should have got it. I was not 100% sure. So I thought it could be an excellent possibility or to...
It can be redone.
Yes, it can be redone. Yes, you are sure. So you get the, I think it's, I mean, it's your birthday.
Okay.
So, congratulations. But I have one complaint over the name. I think it was, I don't know if you know what the Swedish dansband is. It's a very typical Swedish tradition. And it sounds little like a dance band or dance band.
It's even better than.
It's even, yeah. So that was my encounter with Börje. And in this strategic research, and I think that also little connect to this Jan-Olof presentation, there it was this kind of collaboration between academia and industry. We had a steering committee which consists of people both from academia and industry. And I think we were interested in the electronic structure. That was the foundation. And then the people from industry had often a slightly different background, and they talked about some other structure, a very small structure, and it was called the microstructure. And they also claimed that that was important, the microstructure. And I think they had a point, and that was that the microstructure is often crucial for the functional properties of the material. So in that case, it's of little importance then. And as a scientist, then you would like to understand the microstructure, and then engineer would like to control the microstructure. So if this is now important, so if you can control it, you could then tailor applications. So then I would like to give a very short presentation here, and that was really a work. I think the collaboration was initiated by this program. And that is about that material that you see to the right, and that is called cemented carbides. And it's a material that is produced by liquid phase sintering. So you sinter the material, so you take a powder, and then you increase the temperature. And then you get the densification, and then you can also have growth. And particularly if you would like to produce nanocrystalline materials, you would like to have very small grains, then you would like to control the grain growth. But these kind of capillary forces, they are, we can say, quite efficient for small sizes. So if you then start with a powder, say with an initial size of 10 nanometer, then that increases by a factor 100. And it's very hard to avoid that. But the people in industry, they know how to avoid it because they mixed in some other particles, we can say. They dope the material. So if you put a little of vanadium carbide into the system, then the size is reduced, and it's a quite large reduction. It's more than a factor 10. And it's not a 5% effect then. And if you would like to have small grains, this is, of course, crucial. So then came the question, what is the mechanism for this? And then, of course, you think about it has to be kinetics. And there is a lot of work here at KTH done on kinetics. But they are also quite strong in thermodynamics at KTH. And I think kinetics has some influence, but actually thermodynamics is quite important here. There are quite crucial thermodynamic aspects involved. And that is due to, and this is, we can say a little of a theoretical claim then, but there are quite strong experimental evidence now. And that is, if you look at those interfaces in the material, and particularly at the sintering temperature, you don't have this, we can say, very clean situation. So the claim is that you have a very thin film produced by this vanadium. And it's very thin, it's only 2 monolayers. And that film then, that is, the vanadium carbide is not thermodynamically stable as a bulk phase. So it's purely stabilized by thermodynamic effects then. So that is the stable situation. So it's stabilized by interfacial effects. So then that becomes little, then we would like to, we can say we have phase diagrams, and now we would like to add this information to the phase diagram. So here is a phase diagram. It's calculated by this kind of Thermo-Calc software. And then you see that to the right you have a region. You see it's the temperature on the y-axis and concentration or chemical potential of vanadium on the x-axis, and the concentration is larger to the left. So for low concentration of vanadium, you have vanadium dissolved in cobalt, and then you reach the stability limit, and then the bulk phase of vanadium carbide becomes stable, and it's a mixed phase. But then something could happen in this region where you have dissolved vanadium. And then we come back to the electronic structure. Then you can do this kind of electron structure calculations. You have to do it, can say you include temperature, you have to include non-stoichiometry and so on, but then you can really predict what happens in the material. So this is the thermodynamic behavior of the material. And then you see that you get a quite extended region where you have a thin film covering tungsten carbide. And then this blue area is where you don't have a thin film, you have only segregation. But it's a quite large area with a thin film. You also see that it's not perfectly red, and that is due to that you have different concentration of vanadium in the thin film. Then, of course, now when you have this, so this should then be an extension of the thermodynamic, the thermodynamic description. Now we can see, can we tailor applications then? And what we have to do then is to add, we have to do some. So for instance, if you now take a mixture and then you heat that, then you can use Thermo-Calc to calculate the chemical potentials. And then you can see where are you in this phase diagram. So here you can see if you go up to 1546 Kelvin, you are still, the bulk phase is still stable, and you see this little green line following the stability line. But then after that temperature, it becomes unstable. Cobalt also starts to melt, and it has melted at 1621 Kelvin. Then it's liquid. And then you can continue in temperature, and you go up to a sintering temperature. And then you can see the prediction here is that at the sintering temperature, you are still in this region where you have these thin films. So the claim is then that these are very crucial for this growth behavior. The tungsten carbide is covered by a thin film of vanadium carbide, and that influences the growth property immensely. If you continue up in temperature, the thin film will disappear then, and you enter this blue region. So I think that is now, we heard, this is also connects to what Jan-Olof said. This thermodynamic description is important, but these kind of properties, they cannot predict by Thermo-Calc. Here you need this kind of electron structure calculations and really predict what happens, we can say. So I think we are little back to the electronic structure. We made an excursion to the microstructure, but we are back to the electronic structure. So I would like to congratulate you on the birthday and on this occasion. Okay?
Good morning. A couple of weeks ago, I made a major success in my life, not in my scientific research, but in search for the past. You can find Korea. Is the laser? Yes. This one, yeah. Okay. And it's almost 20 years ago, probably the first electronic structure calculation workshop in Korea, and I can recognize, well, there are some Koreans. It's held in Seoul, and this is myself. And Richard Martin, Stephen Louis, I think this is Warren Pickett and Terakura from Japan. Anybody recognize this guy? I don't know. It is Richard Nees. Ah, okay. Okay. So this is my major rediscovery of the forgotten past. Okay, so congratulations, Maria. I already finished my most important part of my presentation. So in the remaining 20 minutes or so, I'll give a less important part. That's introduction of the research on hydrogen storage in Korea. Well, in US, I think these days the emphasis shifted from hydrogen to more batteries in terms of the renewable energy or the future cars. However, in Korea, the effort to use hydrogen for cars and, of course, for other energy source is continuing. And for example, that's a long time ago, 3 years ago, President of Korea introduced this hydrogen, this electric car, fuel cell powered by hydrogen, and introduced this car to the Asian Summit. There was a meeting in Jeju Island, Korea. But it continues last year, Hyundai, which is the major car industry in Korea, it joins the SHHP, which stands for Scandinavian Hydrogen Highway Partnership, and exchanges the Memorandum of Understanding at Swedish Embassy in Seoul. 4 countries consist of this SHHP. Well, this you can recognize that at that time, this person was the ambassador to Korea, and anybody knows him. And then Norway, Sweden, Denmark, Iceland. And 2 months ago, Hyundai announced the production of 1,000 hydrogen cars and export to Denmark with this year. I don't know how it's going on, but there is this big the announcement and the press release. And the price of this hydrogen car is reduced down to still 100,000 US dollars. But 10 years before, it starts from $1 million. It's a significant reduction. And it runs, well, it uses compressed hydrogen gas. Well, the gas tank is a little bit bigger than the usual gasoline tank, but still it runs for 400 miles per tank. So it's at least as good as the gasoline-powered cars. And more recently, that's less than a month ago, Hyundai Norway, I think there is a company called HYOF. I'm not familiar with the name. They exchanged the MOU on hydrogen cars and stations. So that's what's going on. And I'll go to more into my own work. There are 3 ingredients in the hydrogen economy. One is heat production, storage, and fuel cell. My research is on this hydrogen storage. There are 4 major methods. One is the high-pressure tank, which is used by most car companies working on hydrogen fuel cell-powered cars. There's also liquid hydrogen tank. This method is pursued by BMW. And of course, this is the major research area, metal and chemical hydride. I think Boria was working on that this as well to a certain extent. Well, I'm new in this field, and I work on absorption nanostructures. And I have many collaborators. The first line is my student. There are more. And fortunately, we have very generous support from this chemical company. And there's a team led by Dr. Dong-ho Kim. And there are also other professors. Shin Kang is materials engineering professor in our university. Young-il Lee, another university. Experimentalist, Bunya Lee, he's a chemist. And there are one more joining the team who is in chemical engineering. So, well, I'm the only theorist. I happen to be the leader of this whole consortium, and the present talk is kind of a progress report on our ongoing effort to design hydrogen storage materials and experimentally synthesize those materials which can be installed onboard cars and operated under ambient conditions. I have very good communications with the experimentalists, and this kind of fusion research, many different areas. Of course, there was language barrier. We physicists use different language from, say, chemists or chemical engineers, but now we have been working on this already 5 years. This is computational details, but I'll skip that. And at first phase, our idea was as a metal decoration on some skeleton materials. In the first paper, we chose polymers, but it turned out it's not practical. Anyway, the basic idea continues. That's the metal decoration on skeleton materials. For example, in this first paper published in 2006, we had the idea of the backbone material. We tried to put transition metal atoms like titanium, and then it turned out after it attaches, well, 3 hydrogen in an atomic form. After that, hydrogen molecules can be attached around here via so-called Kubas interactions. And we did a lot of calculation to calculate the binding energy of those hydrogen molecules on this system for different choice of geometry and the transition metal atoms. And we include, it turned out we need very high accuracy. So we include 0.5 vibration energy, and we add some ad hoc terms for van der Waals interaction. And it also, spin state is important. As more and more hydrogen molecules are attached, there is a transition from high spin state to the low spin state. Eventually, a spin state is 0. The idea we have is the following. Suppose we have a certain host material. That's what we are designing and what we are trying to synthesize. At high pressure and low temperature, there is very high probability that those hydrogen molecules are attached. So it's a choice between gas phase and observed phase. So there is a very large probability of absorption if you raise the pressure and lower the temperature. That's for the storage phase. When you store it, you want to store as much hydrogen as possible. When you actually deliver it, when you release hydrogen to use as a fuel, the idea is very simple. We raise the temperature and lower the pressure. Then the probability decreases significantly. And this is the released hydrogen, and that's the part we are using for the fuel. And that amount can be calculated from equilibrium statistical physics, or you can perform Monte Carlo, grand canonical Monte Carlo simulations. This is the condition. For absorption condition for storage, after we talked to people in car industry, we chose 100 ATM and 25 degrees C. If it's lower, then it's even better. But we want to store it at room temperature or lower. This is still the safe region. If the pressure goes above that, they regard it's not very safe. For the desorption condition to release the hydrogen, we chose 3 ATM and 100 degree C, which can be conveniently achieved within the car. And we calculate chemical potential in each phase, and it turned out the optimal binding energy for hydrogen molecules should be in between these two numbers. So about 0.3 eV or 30 kilojoules per mole is most ideal for practical hydrogen storage. And we can achieve that with transition metal atoms. However, in practice, transition metal clustering and material degradation observed. So we never succeed making this kind of storage material using any polymers. So we gave up the polymer. Well, that's its binding mechanism. I think I'll skip this, the more theoretical part. So we chose MOF as backbone materials because MOF has crystalline structure, so they're analyzing the details, spectroscopy and others. All these things are very convenient. And to suppress the clustering of transition metals, we use, to make a long story short, we use the functional groups. And this is a typical MOF structure. It has a cubic structure. It has a lot of empty space. And with this simulation, we put transition metal on top of MOF structure. And after all this simulation, and we brought this idea to experimentalists. And because it's a solution chemistry, we cannot decorate the material with bare the metal atoms. So they introduce so-called OMP, Organometallic Precursor. Suppose we want to dope titanium, then there are ligands around it which protects this. And we already have some kind of a functional group, and they interact, and this titanium is attached here. And then we want to remove this by a certain process. So it's still ongoing effort. We succeed up to this point. We want to get rid of this and replace this by atomic hydrogen. This is not the hydrogen we are using. The additional H2 molecules can be attached to via Kubas interaction around here. That's the hydrogen we can use for the practical purpose. And this is the sample, and but still contamination is a big problem, so we have different strategies, but I would skip all this. We are still trying 4 different methods. And also for the skeleton material, we are considering carbide-derived carbon like this, which we already made. Also, we are working on the graphite oxide. Graphene is so popular, and there are a lot of research going on, so we want to insert things inside and store hydrogen in between. And also some biomaterials still in progress. So in conclusion, I introduced some efforts in Korea to make hydrogen storage materials, and these are the summaries. Thank you very much.
Dear friends, ladies and gentlemen, this will not be a scientific presentation, even though I will touch upon the subject, but I will not go into details. This is not my field. Sorry, I just gave another talk. I think it was about 10 years ago that you came to KTH. Is that true? As a guest professor. And Börje, as a professor in physics, did not go into the Department of Physics. Instead, he entered into the Department of Material Science and Engineering, which is much more applied science, with lots of connections traditionally to the steel industry in Sweden. And you may wonder why wouldn't it have been more natural to move into an environment with this sort of the same type of people? In retrospect, I think it was a very wise decision. It has been a very, very fruitful move to combine the more theoretical physics with the more applied material science. So it has been a very, very nice development after this move, and lots of connections have been made between theoretical physics and applied sciences. Just a few examples. We have at this department over the years developed not we, but the department, have developed a software which is now commercialized. It's called Thermo-Calc. It's a software where you can, or a database and a software where you can make predictions, connections to thermodynamics of alloys, and also simulate diffusion processes. And the database has built up over the years based on lots of experimental data, of course, measuring properties of different kinds of constituents, and in this way building up the big database. But what has happened in later years that it's not only experiments, we can also do numerical experiments. Some experiments are very difficult to perform, and instead we can simulate from the basics of physics and simulate thermodynamic properties, and in this way expand the database by not only based on pure experimental data, but also made on numerical experimental data that come from calculations. And this has been very fruitful, I think. I myself is a professor in material mechanics. I have some knowledge about the field, but I'm more from the continuum mechanics side. And from that point of view, of course, there is also lots of interest to look into more details in material behavior. Maybe not into the atomic scale, but still there is a big issue of connection different scales from the continuum to maybe the microstructure of a material, and then from the microstructure into the atomics and dislocations and everything. So I myself had been working in the field, but on the other end, from the continuum mechanics to the more connection to the microstructure. And I think this with the multiple scales is something that has become more and more important, and I still think that there's lots to do in this field, all the way from atomics and electronic structure all the way up to continuum mechanics. Since you came here as a professor, I was a professor myself at that time, so I was not informed in detail. But anyway, if you're looking back, we have now a group of about 40 persons here at the department around Börje, and quite a lot of very qualified persons. There are five professors now in the field, and 2 other in the faculty, an associate professor and assistant professor level. About 5-6 postdocs and more than 20 PhD students. So it's really become a very strong unit at KTH. This has also resulted, it's not, of course, not the result of KTH, but a sort of collective production from Börje. He was one of the first to receive an ERC senior grant about 5 years ago. So it's very easy to be impressed by Börje. One example is that he was advisor and examiner of Gu Bingling, who later became the president of Tsinghua University. So that's quite unusual. We have a professor, he was the advisor to the most prestigious Chinese university, the president of the most prestigious Chinese university. I have get to know Börje a bit since I became president of KTH, and I've also traveled with him to China, so we have had some time to discuss. I know that when he finished the high school with extremely high grades, he was approached by the CEO of ASEA, the company that later became ABB, when they merged the Swedish company ASEA with the Swiss Brown Boveri into ABB. It was a very famous director at that time, Kurt Nicolin, who approached Börje when he was quite young. If he should not start at ASEA, he would get very good conditions, a trainee, and he would have a bright future within the company. But I'm glad that you didn't make that choice, even though I heard that you would. You said it would have been interesting to see what would have happened. But I'm glad that you stayed within the academy. personally, I think that Börje is a very positive person, interested and energetic. You're a good friend of mine. I hope it's vice versa. I think so. And I think one very good thing with Börje, he cares a lot about the people that he works around him. I know that he cares a lot so that each individual should have a good career, and he's looking around where could the next best spot be, or could we secure some money at KTH to secure this person and so on. So it's not just in science and within KTH I have a good connection with Börje. He also comes from a part of Sweden where I grew up, which is called Dalarna or Dalecarlia. So we have lots of common. Of course, we like this part of Sweden very much, and I know he has a summer house there where he very much likes to go. And we also like the ice hockey team from this part of Sweden. Actually, the town where I grew up, Leksand, was a very good team. It's still somewhat, but we are fighting to come back again. So I was thinking about ice hockey players in Leksand that have sort of a common with Börje, and it's sort of make a parallel with sports and academics, which is not bad any time, because it's sort of really individuals that make up a team. But this is not perfect. But I was thinking about Nisse Nilsson. You are the double Nisse. You are the double Nisse of KTH. This was a player who was extremely successful. Sweden won the World Championships in 1963, and in 1962 they beat Canada at that time, which was a really big event. And Nisse Nilsson, this double Nisse, made the final score. Anyway, he had a very nice career, and then he moved to Leksand, this little town, sort of later part of his career. And in this way also brought the team of Leksand to the Swedish championship. So I think that's sort of not very good, but some kind of parallel. You had an extremely nice career, and then you moved to KTH sort of in the later part of the career. So I hope that we can join now to see Leksand in ice hockey next winter, because one of the Stockholm teams went down to the series where Leksand is. So on the 18th of November, it's Djurgården and Leksand, and then I think if we can, you make a note there. So anyway, I hope you will have a nice day here today. Unfortunately, we have this research evaluation exercise at KTH this week, so I'm sort of busy with other things. Maybe I show up in the afternoon, but I cannot promise. Thank you.
I'm very honored to be here, and I would like to tell a little bit from my personal perspective. I think in the program they said we should do the early days. So let me take my personal view of the development in the last 40 years. And what I like to do is, at the beginning, what we have heard already, that you combine different aspects. Takes quantum mechanics, computer, software, material sciences, which I pick out as one example. And let me go back to the 60s. I attended the summer schools in Sweden with Per-Olof Löftin, and I think my generation, many people have really benefited to learn quantum mechanics in that period. So there were basically two schools, the Swedish school, Per-Olof Löftin, and there was the other school, which was in England, in Britain. But this was certainly very basic to learn about concepts. So what did we learn? Perturbation theory, group theory, symmetry, molecules, solids. But it was formalism, so to speak. And then you also had people like Hedin Lundqvist, and which later on reached with Walter Kohl density functional theory. Also relativistic effects, which played an important role in your scientific work. So it was basically, to a large extent, it was formalism, concepts, theory, which is extremely crucial. Let me go to computers, and I'll just give you an example in a minute. The computations were rather limited because the computers were lousy, and I'll show you some example. And I was visiting professor in Uppsala in 78, and at that time, I still remember that computations were not highly appreciated at that time. So times have changed. At that time, it was formalism, and you learned about perturbation theory, then it was a great thing. But if you do computation, that was not appreciated. And certainly, some people claim the whole field has only benefited because the computer power has increased tremendously, which is true, but it's only part of the story. There are many other aspects which need to be done. It was, for example, software development, DFT, various functional properties. We have heard many examples today, parallelization, efficiency, and so on. So, and then what we can do, go material science from very small cases, which was 40 years ago, where you did an element, 1 atom per unit cell. Now we can do 1,000 atoms per unit cell. And again, I'll show you one example of such a development. Let me go back my personal view in my history. I got my PhD in '68 in chemistry, so it was 1 year earlier than Börje. And we heard about the quick time of publication. If you look at this paper, which was the X-alpha method, it was submitted in December 1990. It was published in April '72, and it was a paper which was quoted many, many times in the '70s and the '80s. So that was the X-alpha method. And this work was done when I was postdoc with John C. Slater, an old picture of myself. After my stay in Florida, where there was a close connection between Lövdin and Slater's group, I moved to San Jose to Frank Herman, to the IBM, and at that time we did the X-alpha beta method, which was the first gradient correction. Now you would call that, so to speak, this is the LDA and this is the GGA. That was already done in the 70s. So there is an early stage which also had to be done to make this kind of developments. So I summarized a few things. We have Ole Andersen here. So we have Walter Kohn, who did the density functional theory, and I don't need to explain it in this audience. Slater, who introduced the augmented plane wave. Ole Andersen, who had the concept of linearized augmented plane waves. So there are many concepts which had to go into the details, and this development led to the code Wien2K, and the 2K stands for the year 2K when it was published. There is a review about now the 2K stands for something else. We have 2K licenses worldwide, so which is nice. And I show you one example, which is if you have a boron nitride placed on a rhodium surface science application, where we did the calculation with more than 1,000 atoms per unit cell. And that should illustrate what can be done nowadays with such schemes. Let me go back in density functional theory, and let me go to Walter Kohn. I organized a DFT conference in '97, and Walter Kohn was the main speaker at this conference. So that was an early stage. A year later, he received the Nobel Prize, as you know, here in Stockholm. And the interesting part was he received the Nobel Prize in chemistry, not in physics. And he gave me a call at that time and wanted to find some example. Where is density functional theory useful in chemistry? And I'll give you one example, because that has changed, but at that time, that was a different story. Now, there was another case, which was 2001, a DFT conference, which was held on a special occasion, which was my 60th birthday. And Walter Kohn was again there, gave a lecture, a plenary lecture. But we had another famous speaker at this DFT conference in 2001. And the special thing was he came twice. He came once as a speaker, and you might recognize the speaker. And after the speak, he had to leave immediately because he had an important meeting back in Sweden. So he left, and you know this person. But the special thing which I still remember after the many years is he came back for the celebration, which was 2 days later, and that was the celebration with Walter Kohn, and he came back, so I still remember this kind of things with Berger. Let me take one more example which I mentioned. Walter Kohn was looking for an example in chemistry, and what he has chosen was a calculation, a molecular dynamics calculation we did, where you have a methanol in the center of a zeolite cage, where you could a 10 picosecond simulation using density functional theory. And without density functional theory, such a calculation would not have been possible. And he presented that here in Stockholm at the Nobel laureate lecture, and that makes you very proud that you have some examples for chemistry with density functional theory. I mentioned computers, and it might have been similar in your experience, but I looked up my history. During my PhD work, I worked on the Boros computer, which was on tubes. It has 4,000 words, which is 16K, not megabyte, not gigabyte, not terabyte, it was K. 4K memory. That was the computer where I did my thesis, and I did an APW calculation. So it is clear why this was not a very powerful machine, and therefore you couldn't do very sophisticated calculation. Now we went to teraflops or the like, and I think we all know the development. But this is not the only thing, but you still should remember that the input was on paper, tape, and so on. So there was a tremendous progress in computer science. So let's take another aspect. If we start, and I think that has been obvious in this morning, you really need many aspects, and I think Berger is an excellent example to do that. To start a group, you really have to do this communication. So he did it in Uppsala, Stockholm, establish a research group. And you really have to start, as we heard this morning, about the communication between industry and basic research. You have to have this combination. And take the interdisciplinarity, and I pointed out the topics: physics, obviously, chemistry, mathematics, algorithm, computer science, parallelization, material sciences. You have to learn all these languages, and only by combining all this expertise, you can really make progress to a very large extent. That can only be done as long as it's done with friendship and with networking or whatever you call it. And I think you are an excellent example that this is really the basic concept. So let me choose one thing. Okay, I had the honor to hand over your doctor's degree, honoris degree of our university in Vienna. And so this is the other aspect, to get recognition. And that was a very nice celebration with our rector and our mayor of Vienna, and there was a celebration. We are going to have a nice celebration today again, but that was a very nice occasion, which I still remember. Let me show you one example which I mentioned, that you can really go to a very large system. And the example I've chosen is this: if you have boracene, this is this molecule, and put it on transition metal surfaces, on hexagonal surfaces, then they form very ordered structures. And the interesting part is, if you put them on nickel or on rhodium, the periodicity of these structures vary by an order of magnitude. So you have 2.5 angstrom or 32 angstroms periodicity. So they're very different. Why are they different? You can map it out. If you do a boron nitride, like graphite, with boron and nitrogen, then you have the total energy as a function of lattice spacing, and you find a clear minimum. If you go to the nickel compound, then the nickel in the 111 surface has a perfect match with the boron nitride. While if you take the rhodium, you have a lattice mismatch of 8%. And this 8% mismatch causes that there is a different structure formed. And I cannot go to the details, but here you have a boron nitride lattice, and underneath you see the rhodium, and here you see that the nitrogen sits to the left, and here it sits to the right, because there is a lattice mismatch. So what you need 13 boron nitride to match 12 rhodium. That makes the system rather big. And the question is, can you calculate it? Nowadays you can, and that is the structure. So you have a nitrogen sitting on a rhodium here, and the next time it sits on top of a rhodium is after 12 or 13 lattice constants. And this is basically the unit cell you have to do. And since you have different orientations, you have regions where the nitrogen sits in a favorable position or in a very unfavorable position, and therefore you get different structure. The favorable position, it sits near the surface, and at this favorable position, it sits far away, so you get a corrugation. So it's not flat, you get a corrugation. Now the question is, can you functionalize it? And this forms very easily, and you may put in gold particles in here and do catalysis, for example, on such system, and this is still work in progress. So things like that can be done. We've heard in one of the talks about the steel factory where you have formalism and you want to study the sigma phase of iron chromium, which causes, we have heard about this in the previous talk, and you have to do simulations which go through very complicated structures. You have disorder, you have all kinds of aspects, and that can be done, and you recognize one of the authors in a recent publication. So let me try to summarize what has been done in the 70 years. And we heard that also from the perspective from industry. You go from trial and error schemes in the past through fundamental understanding of the atomic electronic structure, and you can do computer simulations, predictions, and you can often not design the most promising material, but you certainly can narrow design space. You don't have to go through the whole periodic table, and you can say certain aspects are promising and others are not. And here theory can do a lot, and computational material science has been established. And now applications, novel materials, and even patents came out of such a field. And that is a tremendous progress that has been made. And if you think about the success of the computational material science, it's due to joint efforts. And let me try to summarize it. And if you take the best from Österreich, Schrödinger, Kohn, and so on, and let's the results by our jubilant expert. And if you omit the little details, then I think we could say congratulations, happy birthday.
Well, I can start to mention that I've known Börje for some time. In fact, we were PhD students at the same time, not at the same department, but this was at the end of the 60s, and we, at that time, there were no PhD courses available, so we had to arrange them ourselves, and that was our first encounter. I will talk about another totally other type of application. Jan-Olof Nilsson, for example, he demonstrated that thermodynamics and ab initio calculations are extremely powerful for modeling microstructure and also quite useful. Now, it's possible to take this one step further to model mechanical properties as well. Now, traditionally, mechanical properties have only been possible to attack with empirical models. But the progress in recent years, I mean, in addition to thermodynamics, ab initio calculations, and the description of the microstructure, there have also been important improvement in the understanding of the behavior of dislocations. And this has really made it possible to use more fundamental approaches to model mechanical properties. And I'll give just one example of that. Now, Börje and his co-workers' enthusiasm to apply atomistic models to real engineering materials that has demonstrated the relevance and capabilities of fundamental models, and that has certainly stimulated us quite strongly to attack and study mechanical properties. Now, I will just take one example, and that's for high temperature deformation. Now, many materials can be described with the help of the Norton equation. It describes the temperature dependence, the stress dependence of the deformation rate, the strain rate. All these parameters are these parameters in the models are generally fitted to the data. And the approximate values of them can be predicted. The stress exponent is of order 5 or higher for alloys, but and the activation energies for pure elements is the same as the activation energy for self-diffusion, but it's higher for alloys. Now, this equation plays it's about the same age as the Schrödinger equation, and it can be said that it's almost plays the same central role for high temperature deformation as the Schrödinger equation for quantum mechanics. Now, to describe the strength, this quantity, the effective stress, is the important quantity. Now, this it consists of you define the effective stress as the applied stress, the external stress, minus the back stress, and this back stress is really the interesting quantity. It describes the influence of the dislocations and the particles, and these are the things making the most important contribution to the strength. This back stress is also called the internal stress. Now, you can measure this back stress. It's by a stress. You have a specimen at high temperature under constant load. You get the typical creep deformation or slow deformation as a function of time. This is illustrated here. And then you allow a drop in stress, and then you can get either this behavior, this a negative strain rate, positive strain rate, or a zero strain rate. And the zero strain rate, the remaining strain here, corresponds to this internal stress. And this was measured a long time back, but people didn't recognize the importance of this. It demonstrates that this internal stress is a function of the applied stress and also the temperature. The lowest temperature gives the highest curve. So it's close to the applied stress, but it's a little bit lower. For a long time, many scientists thought that the internal stress could be handled as a constant, and that's totally inadequate. Now, to model the influence of particles, which is the most important thing, is that you consider how dislocations climb across particles that can take place in many different ways. But in fact, the critical step here is actually the time it takes for the dislocations to pass the particles. And if you take that into account, the modeling, you can have, in fact, describe the creep behavior of materials at higher temperatures. And this is now an illustration of a computed back stress as a function of applied stress. And the first thing which is immediately obvious is that the behavior is quite complex. This is the influence of the dislocation, and here is this influence of the particles. And here you can understand why people some time ago, and it's in fact even in some textbooks, they thought that this back stress was just a constant quantity. And but in fact, if you take the dislocations into account, it can never be a constant. And this is at a stainless steel at 650 degrees. So if you go to a high temperature, the behavior is quite different. So you see, it's quite a complex behavior which you can predict with modeling. And why do we believe that this is a reasonable description? In fact, we can describe the dashed curves are the experimental values for the life of creep life, stress versus creep life at two temperature. And you can see we can model this in a reasonable way. And later on, this has been a sort of approach has been applied to many different materials. Here's a type of material, 9-chrome-1 moly vanadium steel, which is quite common in modern power plants. And here we can see the different contributions from subgrain boundaries, from dislocation hardening, and from particle strengthening. And if you add all this up, you can describe the total strength of the material. And that is most valuable result. You can also describe the creep strains, the deformation rate as a function of time. The final stage is not modeled here in this case. It's only this up to a constant level here, but you can see that you can describe this sort of behavior quite well. This is at 600 degrees at various stress levels. You can also use the same type of modeling approach to describe tensile stress strain curves. This is in fact for copper with a small amount of phosphorus. It's used for nuclear weight storage canisters. And you can see here you can model the experimental values quite well. You can also describe the strain time curves for copper here. See, they have the experimental values and the model values, and you get, and as in the previous slide, this covers quite a range of stresses and temperatures. So I'll come to my summary. Now, we've been seeing here that we can extend the thermodynamic and ab initio modeling to cover mechanical properties as well using fundamental approach without any fitting parameters. For all the results I presented, there are no fitting parameters involved. And we've seen that this has been possible for predicting creep rupture curves, creep strain curves, and tensile stress strain curves. It can also demonstrate that this sort of fundamental approach can be suitable for long-term extrapolation. I have not demonstrated in this paper, but that can be handled. And all this is very important for several reasons. Of course, if you can model the mechanical properties with fundamental models, you get to develop a much better understanding of the mechanical behavior of the material. But it's also technically highly important for future power plants, for instance, ultra supercritical fossil-fired plants, and also for fourth-generation nuclear plants. We have a design life for 30 to 80 years. And to extrapolate the mechanical behavior to such times, you need these fundamental models. You have no chance of, you cannot test for 30 years. I mean, you cannot wait for 30 years extrapolate from that. That is not possible. And of course, this time factor is, of course, even more important for handling of nuclear waste. And the nuclear waste should stay intact for 100,000 years. And to handle that, you need these fundamental models to make predictions for over a long period of time. Okay, thank you. And thank you again, Börje, for all your stimulating work. Thank you.